Yeah,
Can I ask
Matt,
you a
right?
Yeah. Can I ask you a question about the homework?
Not one of the homework problems. I'd rather do that outside of class because then we'll just, we don't have a lot of fluff like math has where they have, 5 classes a week and 5 hours a week and then they could go over homeworks and stuff. Okay, next thing I want to tell you is, those of you who took engineering materials, you learned that it was a qualitative class, right? Why would you choose a plastic over ceramic? You have to describe why you would choose it based on its properties. This class is a number crunching quantitative class. You've seen it so far, just like math and physics. The more problems you do, the better you do. So what I've done in the past with statics, and I'm going to do this semester, is I'm always going to take the exam problems from the textbook. The exam problems are always coming from the textbook, which means you know that one of the problems in the textbook, or 4 of the problems in the textbook, are going to be on the test. So what am I trying to encourage you to do?
Do a lot of problems.
Do extra problems. Don't just do the homework problems. Do them all. And maybe you don't have to crunch all the numbers of all the problems, but set up every single problem. And we're going to start doing setup today. So you're going to see the steps that we're going to go to. And I'm going to keep the solutions to the textbook in the STEM Center. I can't just leave it there because it could walk, but what I'm going to do is leave it in the tutoring room, and then you could check it out for a time period and then put it back in there. Does that sound good? So when I took statics, I worked through every single problem in the textbook before I came into the exam. My experience is students who just do the homeworks usually get a B or maybe a C in the class. It's only if you do extra problems that you really have a chance with an A. So you have to do extra problems. So it's really great to work in groups and everybody go, okay, let's do problem 3, let's do problem 4. And like I said, you don't have to work through the whole math of the problem because the math you know how to do. It's setting up the problem. Okay, so we're starting, for that quiz, did you get a resultant value? You got a value. Was the value 0? No. So was this really a statics problem? Was this quiz a statics problem? No. There was a resultant. There was a value. This thing was going to move. Was it? What are the 2 different types of motion? Translational and rotational. What kind of motion is it having?
Translational.
It's translational motion. Let's take a look at the problem one more time. How do you know it's only translational motion? All 3 forces are coming out of this point, and this force is pulling it in that direction, this force is pulling it in that direction, this force is pulling it in that direction. If we were all touching something in one spot and pulling on it in 3 directions, what kind of motion is it going to have? Translational motion. It's only if we're applying forces in different points that we're going to cause a rotational motion. So we, in the end here, found a resultant force, which gave it some kind of translational motion. So even though you did this problem in a statics class, it's really a dynamics problem. It's moving. And all statics courses, the textbooks, they first want to make sure students know how to find resultants. So even though it's statics, we did a dynamic problem first. Then once they know that you're comfortable with finding resultants, then they move on to statics problems, where the resultant motion is 0. Okay? So we're moving on to statics now. Okay, this is the first time I've taught in this room. It's kind of a long room. If I'm over here writing something, you guys may not be able to see it. And if I'm over there writing something, you guys might not be able to see it. So you have to tell me, Joanne, I can't see it, it's too small, too big. Also, the screen is a little bit too far out, so I think that there actually could be some view block, so you have to clue me in. I also noticed that this screen is not really centered to the room, right? The 2 screens are centered, and when I'm on Elmo, I'm very far from you guys. So let me know as we go along what's comfortable. I thought that even if I'm working here at the Elmo, I'm going to have the screen over there so it's somewhat central. So, we're talking about statics now. What are some forces that act on bodies? What are forces that we're going to be looking at? What kind of forces act on bodies? So I have a body here.
Gravity?
Gravity. Okay, is gravity a force? No, so what is the force?
Force of?
Okay, force of gravity, which is called? Weight.
Sorry.
So the first one is weight. Okay, so we don't use mass. When a problem gives us mass, the first thing we do is convert it to weight. Mass has nothing to do with us. We want weight. We always are dealing with forces. They give you mass, you multiply it by g. Because if you put m into the equation, you're going to get the wrong answer in the end. Okay, so weight. So one force we know of is weight. We'll just say that it's equal to mass times gravitational acceleration. And what is the direction of weight? It's always down. Down and away from body. What are forces? Are forces vectors or are they scalar? They are vectors, which means they have a magnitude and a direction. So not only do we need to know the number of the weight, we need to know the direction. So weight is always down, away from the body. What's another force? Tension. Oh, and what variable do you think we use for weight? W. Should we use W always? Yes, let's be consistent. Weight is W, period. If there are 3 weights, do it W1, W2, W3, do WA, WB. Use capital W. Okay. How about tension? What do you think the variable is going to be? T, capital T. So let's put a little cable here connected to a ceiling. So how do I draw tension?
Force away from the.
It's away, it's drawn, and actually I should put, hang on a second. We're going to do it so it's actually going through this. So tension is drawn away from the body, so tension is away from body, and it's along the cable or the wire or the rope or whatever it happens to be. So you find where the cable is or the wire and you draw it away from the body. Can you guys see over there even though I'm here? Okay, what's another one? Weight, tension. Normal. What should we call a normal? What variable you want to use? Capital N. Everybody in agreement? Weight W, tension T, normal N. So let's say that there is a surface right here. So Joe P, tell me how I would draw my normal. I would draw it towards the body. And what's its direction? Perpendicular to the surface, right? So it's got to be perpendicular to the surface and towards the body. Looking at the direction that the tension is drawn and the normal is drawn, what can you say about a normal force? Is normal a tension? What is it? What's the opposite of tension?
Compression.
Compression. Those of you who took materials again, third of you. The opposite of tension is compression. We're looking at this body over here. I'm trying to draw, don't think I'm going to be able to draw it exactly the same way. And I have its weight going down away from the body. I have the normal going towards the body. And I have the tension going away from the body. The tension is pulling it. The normal is compressing the body. In class, people have asked me in the past, in statics, do I have to draw it towards? No. If you prefer to draw the normal here instead, that's fine. You don't have to draw it here. Did everybody hear that? But I want you to realize that it's a compressive force. This is really where it is. Okay, but you can draw it here if you want. And you only draw one. If you draw 2 of them, if I leave this free body diagram the way it's drawn, then it looks like there are 2 normals. You can only draw 1. So we have weight, we have tension, we have compression. I'm going to put up here, sorry, we have weight, tension, normal. I'm going to put compression. and it's towards the body. And what do you think, how do you abbreviate compression? What variable? What do you think? C. What other forces did you deal with in physics? Friction. What variable did you use in physics? F, but did you call it a small f, right? Because a large F usually means...
Well, then there's two. There's static friction and there's
Right, but did you use a capital F or a small f? Usually small because capital F implies force. Capital F represents force, so yes, and then Paul, you're right, there's either static or kinetic. Which one do you think we're going to be using in this class? Static. It's the friction that the force that just overcomes the friction that started to move. So what is the direction of friction? Okay, it's opposite of the motion, and what else? It's parallel to the surface, no? So if I wanted to draw friction, it would be parallel to the surface, and then I have to decide which way it's going to move. Well, if this cuts off and the weight here, it's probably going to go, the motion's probably going to go down. So I'm going to draw the friction here. Armando, question?
No, can't see cut below the compression because the monitors.
Okay, thanks. Okay, so we wrote down friction. And we said that it's perpendicular, no, it's opposite of the motion. And it's parallel to the surface. And we said that the variable we use is small f, and it's either static or kinetic.
Joanne,
Yeah.
I don't understand what's with compression. Isn't that the same as the normal, or is that another?
Yeah, so good question. So normal is one example of a compressive force. So right now we have this coffee mug right here, and its weight is going down, and the normal from the table is compressing the mug. It's going up. But a normal is only one example of compression. In your hand. Well, I guess this would be a normal too. How about if I take your arm and I'm pulling your arm and you're feeling the load in here? There's some compression and tension going on because we have a ball and socket joint. So would we call it a normal too? That might be a normal too. I'll have to think of another one. But I would say in general there are compressive forces and normal is just one of those. But let me think of another compression.
Yeah, this
Okay.
would be a force, technically. That would compress from the top, not just the bottom.
Atmospheric pressure, maybe, but I mean usually like, how about a snow load would be a compression, but then it's weight that's going down too. So what I'm trying to describe is the direction of them, but as we go along we're going to find some other examples. Okay? Okay, weight, tension, normal, compression, friction. I have to draw my friction over here. So it's going to be parallel to the surface, and it's going in the opposite of the motion. Any other forms you can think of? I think we labeled all the ones we could think of. So now we're going to start doing problems. Okay, so in your packet, we're on page 11 in your packet. We're starting to learn how to set up these problems. So we're setting up, of static problems. I think as engineers we tend to love pictures. Words we don't like as much, maybe. I went to a meeting yesterday with the art department, and we were talking about a budget of a future class, and they had no table showing the numbers. It was all this essay that I had to keep finding numbers in it. I was like, oh my God, I can't be with anybody from engineers. So We do only like pictures, we like graphs, but words are important too. And whenever you do these statics problems, you have to read the words because there's information in there that can't be provided in the picture. So let's read through it. Well, let's look at the picture first. We have this cylinder. It's resting along a surface. There's a cord on it. The cylinder is suspended from the ceiling. So it first says, a homogeneous steel cylinder weighing 500 pounds. So why are they telling us that it's homogeneous?
Because it's a cylinder.
It's uniform density, uniform mass. We know that the weight's going to be dead center in the middle of it. Okay? And whenever a problem is given for me, I always write on the picture as scrap. So far they told me there's weight. So I'm going to put weight going down, 500 pounds. It says it's supported by a flexible cable. Why the hell would they tell me it's flexible? Not necessarily. Let's find a flexible cable here. What force can a flexible cable not take?
Compression.
Compression. Can it take tension?
Yeah.
Yes, it can't take compression. If I wanted it to take compression, I wouldn't use a flexible cable. I would use some kind of rod or link, right? So they're telling you that it can't take compression. So it's definitely going to be tension. So we know now that there's also tension here. And we can see that there's tension also, right? There's a here. And I'm looking at the cylinder, so tension's going to be drawn away. And then it says that it's a smooth inclined plane. Why is that important?
No friction.
No friction. Determine the tension in the cable and the force R exerted by the inclined plane on the cylinder. So we already know that we call weight W, we call T tension. What are they talking about in terms of R? What's R? The normal, right? It's what is the surface applying. So how am I going to draw that? I'm going to draw it like this, right? Going towards my body, and I'm going to put my normal. So now we're going to make up a table. The table is going to say force, magnitude, direction. And you guys remember, it's being filmed right now. So you decide, is it important for you to write every single thing, or is it better to get it from the video? You choose for your learning style. Is it better for you to write, or is it better for you to listen? Everybody's different. Okay? Now, chances are, maybe the video will get busted. I don't know. But just don't spend a lot of time writing if you feel like you're not absorbing what's going on. Okay, so we have a table, and we're going to do this on every single problem. So I'm going to start going around the room and asking you. Rather than calling out to you and having you respond, I'm going to go one person at a time. So Richard, we're going to start with you. And if you want to pass, you can say pass. Richard, what's one force in this problem? Weight. Do we know its magnitude?
Yeah.
Yes. Do we know its direction? Yes. So those two things are knowns. Remember, this is a vector. A vector has a magnitude and a direction. We know the direction and we know the magnitude of the weight. David, next. What's another force? Tension. Do we know the magnitude? What?
Actually, yeah, with the angle.
No, then you have to calculate it. So the question is it given? Is it given? No. Do you know its direction?
Yes.
Yes. What's Eric? What's another force present? Normal. We're going in order, sorry. Eric W. Do we know its magnitude? No. Do we know its direction?
Yeah.
Yes. Any other forces, Jill, or are those three the only ones? Those are the only ones. So how many unknowns do we have here? Two unknowns. We have two unknowns. If we have a problem that has two unknowns, how many equations do we need? Armando, if we have a problem and there are two unknowns that we have to solve, how many equations do we need?
Two.
Two equations. Armando, which equations do you think you're going to use to solve this?
Some of the forces.
Good. Which ones? You need two of them.
Some of the forces in the x and the y.
Right. And you have to give me an equation, so you only gave me the left side of the equation.
Mass times acceleration.
No. Yeah, okay. And then what does mass times acceleration turn out to be, because it's a statics problem?
0.
0. So sum of the forces in the x equals 0, sum of the forces in the y equals 0. So we can get two equations from one body, right? Right? If we have two unknowns and we need two equations, we need to have one free body diagram. Does everybody agree? Because Armando told us we only need two equations. Sum of the forces in the x, sum of the forces in the y. So what is my sketch here? That is not a free body diagram. This is scrap. I just wrote on there, I'm never even going to look at the scrap that you do. The drawing right on the picture. What do we want to draw a free body diagram of? So, JJ, what do you want to draw the free body diagram of?
The cylinder?
Good, cylinder. Can we just say it's a point?
Sure.
Sure, because it's homogeneous. So what forces should I draw looking at the picture I have up there? I have weight going down, and what's weight equal to? 500 pounds. I have my normal, which is going up here. I'm going to put directions in a little bit. And my tension going here. So everybody, here's first trick. Well, not trick, you already know this, but take a look up here. I know that this is given as 75 degrees. This is a horizontal surface. So if I draw this line, this is parallel to this. So isn't this right here 75 degrees? These are alternate interior. Okay? So I'm going to go back here and write 75 degrees. Okay, this one is the one people usually just learn. They learn in statics, not in physics. So, we have, see now you're not I'm not being filmed. We have a horizontal surface that's at an incline of 55 degrees. And I'm drawing a normal that's perpendicular to this surface. And I need to find out where is this 55 degrees. So if you remember back in geometry, look at this. If I have 55 degrees between these two hands, right? Lily, would you put two hands perpendicular to my hands? So he's putting, take this one and put it perpendicular, right? And now put the other one perpendicular, the other hand perpendicular, right? The angle between those two, if you go up here, the angle between those will be the same. So if I have two lines, and I know the angle in between, the angle in between two lines that are perpendicular to these lines are the same as well. So looking up here, this 55 degrees is between these two. What's perpendicular to this line? This. What's perpendicular to this line? This. 55 degrees is right here. Let me do it again. We know this is 55 degrees. This green line is perpendicular to this. This green line here is perpendicular to the horizontal plane. The 55 degrees is here. So here is the 55 degrees. Is my free body diagram complete? There's something very important missing. What's missing?
Axes.
The axes. What axis do I show? All of them? Yes, but only the positive side. So here's my positive x-axis, and here's my positive y-axis. On Tuesday, I gave you a summary sheet. I don't know if you could pull it out quickly. The summary sheet had the reason for using cosines, all the stuff about units. Notice on the page it says, on both sides, it says free body diagrams. You can look at either side you want. Free body diagrams, you have to have the x, y, and the positive x, y, and z axis labeled. Do I have the positive x, y, and z axis labeled? This is a 2D problem, so I don't need z. It's good. Next, The forces need to be labeled, either with variables or magnitudes. Do I have them labeled? Here's T. It's labeled with a variable. Here's the normal, labeled with a variable. Weight, labeled with its magnitude. That's good. And what, Kyle, could you read the last one?
Force direction.
And the directions of the forces have to be shown. Did we show the direction of the tension? Yes, by putting the 75 degrees in. Did we show the direction of the normal? 55 degrees. We're done. This is the setup of a statics problem. You read through the words, you find out what information they're giving you. You draw your scrap if you want to. I like to draw the scrap, draw all the forces in the picture. You write a table. The table has to have the forces present, its magnitude and direction to determine what's known and what's unknown. Once you know what's unknown, then you know how many equations you need, and then you know how many bodies you need to solve for. Last thing, you draw the free body diagram of the body in question. You've done this before. I don't know if you've done it as meticulous, but you've done it before. Let's do another problem, the one on the bottom now. Okay. Brandon, right?
Yeah.
Okay, we're up to Brandon. Okay, the cable system shown in the figure is being used to lift body A. Could everybody see where A is? It's this thing. It's the block. The cable system is in equilibrium at the cable position shown in the figure when a 500 Newton force, so they're telling us there's 500 Newtons there, but they also show us where the 500 Newtons is, right? So far we haven't gotten anything out of the wording. And it's applied at joint 1. Determine the tension in the cable A, B, C, D, and the mass of body A that's being lifted. So, let's draw our table. Force, magnitude, direction, and it's Brandon, right? Not Brendan.
Yeah, Brandon.
Brandon. Brandon, could you tell me what forces are present, one at a time?
Okay, so there's the weight of A.
Okay, so the weight of A, do we know its magnitude?
No.
No. Do we know its direction?
Yes.
Yeah, it's going to go down, right? Okay, another one.
Then there's the force of 500 newtons.
The 500 Newton force, do we know its magnitude?
Yes.
Direction.
Yeah.
Okay, let's go on to Chris. What are some other forces that are present?
Tension and B.
Okay, the tension in B. Do we know the magnitude?
No.
No. Do we know its direction?
Yes.
Yes. Another one?
Tension C.
Tension C, magnitude,
No.
direction.
Yeah.
And any more?
Tension
Tension A. No magnitude,
A. No.
direction?
Yeah.
Okay.
And D.
And tension D. Do we know its magnitude? For now, we're going to say no. And its direction, yes. So I'll wait until everybody writes that down first. Okay, Hughes. Let's look at tension D. Do you know what the value of tension D is?
No.
Okay, they don't give it to us, right? But can you figure out by just looking at the picture? Because there's this cable, it's going vertically down, and then there's a weight suspended here.
Yeah.
What is it?
B 500.
It's whatever the weight is, right?
Yeah,
The
right.
problem above had a 500-pound force, and now we're having a 500 Newton, but it's over here. We don't know what the weight is. But does everybody agree that the tension in D is the weight of A, right? So what we're really doing is we're doing a free body diagram. Let's erase this. We're drawing a free body diagram of that link right there. And what's the link? It's 3. And we have a weight of A going down, and we have a tension. Which way should I draw the tension? Mark.
Going up.
Going up. TD. And wouldn't you say by saying sum of the forces in the Y is equal to TD going up minus WA going down equals 0, and isn't TD equal to WA? Mark? Yeah.
Yeah.
Right? Everybody agrees with that? But I'm not gonna make you do this. We're gonna know from now on in class, we do not have to draw a free body diagram from that. If you have a weight that's suspended from a cable, we automatically know that TD is equal to the weight. Okay? So I'm gonna go back over here, and I'm gonna cross the sucker out, and I'm gonna put TD right next to it. Everybody good with that? Because there are more important free body diagrams for us to draw, not that one. Wes, how many unknowns do I have?
4?
I have 4. I have 4 unknowns. If I have 4 unknowns, how many equations do I need?
4?
4 equations. If I need 4 equations, what equations do you think we should draw? We should write. These are 2D problems, right? So what equations do we have available?
Some of the force?
Which ones? Some of the forces in the,
X and Y?
and they're equal to 0, right? Giving me the whole equation.
Yep.
Some of the forces in the x equals 0, some of the forces in the y. But that's only 2 equations, and I need 4. So how many bodies am I going to need to analyze?
2.
2 bodies.
1 and 2.
Good. Point 1 and point 2.
Yeah.
So if we go now and draw, we have a couple minutes. Everybody draw a free body diagram of point 1 and 2. So I don't know if you want to move that. Maybe move it away. Just hold it. Just have a minute, so I just want to finish this up. So we learned that weight goes down, right? So weight in joint 2, it goes down, and I wrote down it's also equal to TD. All the tensions are drawn away from the body, right? Because they're tension forces. How are the free body diagrams? Do I have the x, y, positive axes drawn? Yes. Do I have all the forces labeled with either variables or values? And do I have all the directions of the forces shown? Yes. So this is great. What if I wanted to draw a free body diagram of this cable that's running from 1 to 2? Chris, L. What would we do, Chris, if I wanted you to draw a free body diagram of joint 1 to 2 with the cable? What forces would I show on here?
Well, we have tension A coming in from
Okay,
point 1, right?
But tension A is in here, right?
Okay.
So what I have is I have tension A going this way from 1, and I have tension A going this way from 2. So what happens to those? They cancel each other. They're equal and opposite. Does it mean that it's not there? Sure, the tension is there, right? It's being pulled. That rope is being pulled. But it's an internal force. We don't account for it in a free body diagram. So Chris, what are the other forces that should still be there?
Well, we still have